Hello, this is Richard Hammack's Calculus 1 course. This is a continuation of Lecture 8. Lecture 8a was an introduction to limits. In Lecture 8b, we talk about limit laws. Before we begin, a few vocabulary words. To evaluate, compute, or find a limit means to determine the number that limit equals. Today's goal is to develop some rules that help us evaluate limits, or to compute them, or to find them, to determine the number that they equal. Let's begin with the definition of a limit from last time. Suppose f is a function and c is a number, then the limit as x approaches c of f of x is the number that f of x approaches as x approaches c. And we looked at this picture last time. Here's a function, y equals f of x, and a number c. And as x approaches c in this picture, the corresponding value f of x gets closer and closer to this y-coordinate of L. You can see that happening here. X is approaching c, and f of x is approaching L. It happens from the other side as well. As x approaches c, you'll see f of x approaching L. So this number L is the limit as x approaches c of f of x. It's the number that f of x approaches as x approaches c. It's understood that this language also applies to functions that look maybe something like this, f of x. Here we have the x value c and the y-coordinate L right there. And as x approaches c, the corresponding f of x value, it's actually getting bigger and less than L alternately, but it's zeroing in on L. So as x gets closer and closer to c, this number f of x is straying less and less from L, in a sense getting closer and closer to L. So in other words, we might say, as reflected in this picture, and also in this one, that the limit as x approaches c of f of x equals L means that f of x strays less and less far from L as x approaches c. But the takeaway is that the limit as x approaches c of f of x is the number, L, that f of x approaches as x approaches c, as reflected in both of these drawings. Let's get down to today's goal. We want to find certain limit laws, and these are rules that help us compute limits. We're going to begin simple. Think about the function y equals f of x equals x to the power of n, a power function. And you're familiar with the graphs of power functions. If n is even, it might look something like this. But take a number c for x and look at the corresponding y value, c to the n. You would totally believe that as the variable x approaches c, the corresponding function value, x to the power of n, gets closer and closer to c to the power of n. That's actually our first limit law. It's a very simple one, and it's totally believable. The limit as x approaches c of x to the power of n equals c to the power of n. As x gets closer and closer to c, x to the power of n gets closer and closer to c to the power of n. Here's another simple limit. Think about the function y equals f of x, which is a constant k. Its graph is just a straight line with slope 0 passing through the y-coordinate k. And pick an x value c. And think about x approaching c. The variable x getting closer and closer to c. Look at the f of x values. They're always equal to k. As x approaches c, not only is f of x getting closer and closer to k, it's already there. So in a very real sense, as x approaches c, f of x is getting closer and closer to k. In fact, it's already at k. We express this as the limit as x approaches c of k equals k. These two equations are our first two very simple limit laws. And we're going to record them, and we'll have a lot more. These are basic limit laws. First of all, the limit as x approaches c of x to the power of n equals c to the power of n. And also, as written here, the limit as x approaches c of k equals k, where k is a constant. We could add a few more to these. Instead of a power function, think about an exponential function. You get the limit as x approaches c of a to the x, where a is some positive constant, would be equal to a to the power of c. As x gets closer and closer to c, a to the power of x would get closer and closer to a to the c. And you could do the same thing for logarithms. As long as c is in the domain of a logarithm function log base a, in other words, c is positive, the limit as x approaches c of log base a of x should be log base a of c. As x gets closer and closer to c, it stands for reason from your understanding of the graph that log base a of x is getting closer and closer to log base a of c. So these are our first four limit laws. A few examples. The limit as x approaches 3 of x squared. Limit as x approaches c of x squared should be c squared. So the limit as x approaches 3 of x squared is 3 squared by this first limit law. And that's equal to 9. Now all of this should sound and look very intuitive and understandable, and that's good. Here's another one. The limit as x approaches pi of x. Let's think about that one. This function x right here is really x to the power of 1. So according to this first limit law, the limit as x approaches pi of x to the power of 1 is pi to the power of 1, which is just pi. That should be totally transparent. It's saying that as x approaches pi, the number x is getting closer and closer to pi. Here's another example. The limit as x approaches pi of 7. Let's think about that for a second. 7, that should be an f of x here, so it's the constant function f of x equals 7. No matter what x is, f of x equals 7. So according to this limit law, the limit as x approaches pi of 7 should be equal to 7 for the constant 7. Here's another one. The limit as x approaches 1 of ln of x. Remember, ln of x is log base e of x. So according to our fourth limit law here, the answer should be ln of 1. As x gets closer and closer to 1, ln of x is getting closer and closer to ln of 1. And ln of 1 is equal to 0. So these four examples, we've evaluated or computed 4 different limits using these very basic and simple limit laws. Let's move on. There are some additional limit laws that turn out to be very useful. We'll tally them on this page. And everything that's on this page, we're supposing that the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist for two functions f and g. Well, given the setup, imagine taking the limit as x approaches c of this more complicated function f of x plus g of x. Well, you would certainly believe, and you'd be right in saying that as x gets closer and closer to c, f of x plus g of x is getting closer and closer to what f of x is approaching plus what g of x is approaching as x goes to c. In other words, it's equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x. So this limit law is, it illustrates something that you'll see a lot with these limit laws. On the left, you have what looks like a fairly complicated function, f of x plus g of x, and you're taking the limit as x approaches c of that. And on the right, it breaks it down into two separate, simpler limits. So in theory, if you're trying to compute this complicated limit, you could break it down into two simpler problems by this limit law. Now, the same reasoning would apply to the limit as x approaches c of f of x minus g of x. It's equal to the limit as x approaches c of f of x minus the limit as x approaches c of g of x. Here's another rule. We have a so-called constant multiple rule. Think about the limit as x approaches c of a constant k times a function f of x. It would equal what k times f of x is getting closer and closer to as x gets closer and closer to c. Well, that would be k times what f of x is getting closer and closer to. In other words, it's k times the limit as x approaches c of f of x. We call this a constant multiple rule. It says that when you're working out a limit, when you're finding this limit, you have a constant k in front of the function, you can factor that k outside the limit, basically making the limit problem simpler. And this is going to be useful. We also have a rule about the product of f and g. This should be very intuitive and believable. The limit as x approaches c of f of x times g of x. The limit as x approaches c of this complicated function, which is the product of f and g. Well, that's equal to what f of x times g of x is getting closer and closer to as x approaches c. And that should be what f of x is getting closer to times what g of x is getting closer to. In other words, it's the limit as x approaches c of f of x times the limit as x approaches c of g of x. So sometimes it's useful to apply this limit law when you're taking the limit of a product of two functions. You can break that down into the product of the two simpler limits, this times that. Here's one that you'll use a lot. The limit as x approaches c of f of x over g of x equals the limit as x approaches c of f of x, that number, divided by the number limit as x approaches c of g of x. This is saying that the number that f of x over g of x is getting closer and closer to as x approaches c equals the number that f of x is getting closer to divided by the number that g of x is getting closer and closer to. This is a very useful limit law. You got to be a little bit careful though, because if it ever happened that the limit as x approaches c of g of x was equal to 0, you'd be dividing by 0 in this law, and it wouldn't work. So this works provided that that denominator, limit as x approaches c of g of x, is not equal to 0. So you've got to be a little bit careful there. Here's another one that we'll see. The limit as x approaches c of f of x raised to a power of n. That's the limit as x approaches c of f of x raised to the power of n. The number that f of x to the power of n is getting closer and closer to as x approaches c equals the number that f of x is getting closer and closer to raised to the power of n. And this is true for any positive integer. And here's another one, completing our set. The limit as x approaches c of the nth root of f of x equals the nth root of the limit as x approaches c of f of x. Basically, this is saying that in a situation like this, you can bring that limit inside the radical. And this is true for any integer n, for the nth root. But we do insist that this thing inside the limit as x approaches c of f of x, that's got to be greater than 0 for this limit law to work when n is even, because if this were less than 0, negative, you couldn't take an even nth root of it. So again, it's sort of like the rule up here. You got to be a little bit careful in applying this sometimes. Let's look at a quick example using these limit laws. And I'll bet you, when you look at this example, the limit is x approaches 3 of 4x plus 5. Even without thinking of these limit laws, I'll bet you immediately see the answer. But still, we're going to go through and apply the limit laws very carefully, just to illustrate them. Things will get more complicated in due time. The limit is x approaches 3 of 4x plus 5. That's the sum of two functions. The function f of x equals 4x plus the function g of x equals 5. So in evaluating this limit, it's the limit as x approaches 3 of an f of x plus a g of x. You could break it up into two simpler limits by this first limit law. It's the limit as x approaches 3 of 4x plus the limit as x approaches 3 of 5. Well, let's work those out. One thing we do here, or can do, we have the limit as x approaches 3 of 4 times x. We can use this constant multiple rule to take that 4 times the x outside the limit. So this 4 can come outside to be 4 times the limit as x approaches 3 of x. And we'll just carry this limit as x approaches 3 of 5 over right here. Now let's work out these two limits to get an answer to our original question. We have 4 times the limit as x approaches 3 of x right there. Now the limit as x approaches 3 of x by one of our basic limit laws on the previous page, that's going to be just 3. This is x to the 1 after all. So the answer to this limit is 3 to the power of 1. And the limit as x approaches 3 of 5 is equal to 5, again by the simple rule on the previous page. So we get 4 times 3 plus 5. This plus that. And that's our answer of 17. So here we've broken this down very carefully using limit laws to get an answer of 17, which you probably already saw because you could see that 4x plus 5, as x approaches 3, it should be getting closer and closer to 4 times 3 plus 5, which is 17. And if you're looking at it that way, that's good. You should look at it that way. But it's also important to be able to break things down with these limit laws because that's going to be useful later. Another quick example, and this example, I'll tell you up front, it's going to be a little bit tedious because we're going to dot every I and cross every T with these limit laws. We're looking at the limit as x approaches 2 of 3x squared minus 4x plus 7. We want to evaluate that. So let's see, what limit law could we apply? We could look at 3x squared minus 4x, that as being a function, f of x, plus another function, 7, call that g of x, and apply a limit law here, the first limit law from the previous page. We get the limit as x approaches 2 of that first function, plus the limit of as x approaches 2 of that second function, 7. So we've broken this one limit up into two simpler limits. Now this simpler limit, the limit as x approaches 2 of 3x squared minus 4x, you could break that up further. This is like the limit as x approaches c of f of x minus g of x. And on the previous page, we had a limit law for that. That's the limit as x approaches 2 of the first function minus the limit as x approaches 2 of the second function. And we'll bring down the limit as x approaches 2 of 7 here. So we have 3 separate limits. For this first limit, the 3 can factor out using the constant multiple rule. And the 4 could factor out here. And let's bring down the limit as x approaches 2 of 7. So we've got this down to this limit equal to the sum or difference of 3 very simple limits. Now the limit as x approaches 2 of x squared, we had a limit law for that. That's 2 squared minus 4 times the limit as x approaches 2 of x. The limit as x approaches 2 of x is 2, so 4 times 2. And the limit as x approaches 2 of 7 is 7 from one of our limit laws. So now we've got something that we can just add together, add up these numbers, and you get 11. So here we've shown that the limit as x approaches 2 of 3x squared minus 4x plus 7 equals 11. Now I told you you wouldn't like the way we solved this because we dotted every I and crossed every T. We used every limit law that applied. I know you can look at this and you can tell that the limit as x approaches 2 of this function should be equal to what you get when you plug in 2. Just plug in the number that x is approaching. 3 times 2 squared minus 4 times 2 plus 7, it's 11. And that's good if you're looking at it that way. In fact, when you are reasoning things out like this, you can see that if you had like a polynomial like this one, and you're working out the limit as x approaches 2 of that polynomial, you could just plug in 2 to that polynomial. And you get that with these limit laws. And we're going to go ahead and record that. If, as in this problem, f of x is a polynomial, then the limit as x approaches c of f of x just equals f of c. So you can bypass a bunch of these limit laws using this theorem or property. So for instance, if you had something like the limit as x approaches 5 of 4x squared plus 2x minus 1, that's a polynomial, the limit of a polynomial, you'd know that to get this answer, all you have to do is plug in this number c equals 5 into your polynomial function. 4 times 5 squared plus 2 times 5 minus 1, and that's 109. So don't worry, you don't have to use these limit laws all the time. There are lots of shortcuts. Here's another example. Let's look at the limit as x approaches 2 of 3x squared minus 4x plus 7 divided by x to the 5th minus 3. This is the limit as x approaches 2 of a quotient. And if you think back to the previous page, we had a limit law for that. The limit as x approaches 2 of f of x over g of x is the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x. So we've reduced this more complicated limit down to a quotient of 2 simpler limits. And if you look at these 2 simpler limits, they're both limits of polynomials. So we can use this theorem up here that says just plug in 2 to those 2 polynomials. Plug in 2 to 3x squared minus 4x plus 7 right here. And plug in 2 to the x to the 5th minus 3. You get 2 to the 5th minus 3. And work that out, and you get 11 over 29. Now you can see from this example that if you ever had a rational function like this one, a polynomial divided by a polynomial, working things out this way and using our theorem up here, what you get is just the number that x is approaching plugged into that rational function. In this case, it's 11 over 29. And let's note that as a theorem that you can use. If f of x over g of x is a rational function and the denominator is not 0, which is important, then the limit as x approaches c of that rational function is just c plugged into that rational function. So you should work some examples in the book where you're getting used to applying these properties. Here's another example. It looks just like our previous example, except we're putting this expression in a square root. Now remember, we had this limit law that said in a limit of the square root or the nth root of a function, that limit can come inside the radical. So this is the square root of the limit as x approaches 2 of 3x squared minus 4x plus 7 over x to the 5th minus 3. And this limit right here, we're going to recycle some of our work. We just worked that up here. That's 11 over 29. So working out this limit inside the radical, you get the square root of 11/29. So I hope these problems seem easy. Nonetheless, work some exercises to convince yourself that they really are easy. Here's another example, a little more complicated. If you look at this, I bet you can see what the answer is going to be, but we're going to work it out with the limit laws. You probably see the answer pretty quickly, but let's work it out carefully just to illustrate the limit laws. The limit as x approaches 2 of x cubed, which is a function, plus this other more complicated function right there. We can use our first limit law to break that up into the limit as x approaches 2 of that first function, plus the limit as x approaches 2 of the second function. Now the limit as x approaches 2 of x cubed, we know that's 2 cubed by one of our limit laws. What about this next limit? It's the limit of a quotient. So another limit law says we can write that as the limit as x approaches 2 of the top, x squared times the square root of x minus 1, divided by the limit as x approaches 2 of this expression on the bottom. So notice how this complicated limit here is getting simpler and simpler. It still has limits in it, but they're simpler limits. Now 2 cubed is 8. On the top, we have the limit as x approaches 2 of a function times another function. And you could write that as the limit as x approaches 2 of the first function, x squared, times the limit as x approaches 2 of the second function, square root of x minus 1. And then on the bottom, we have the limit as x approaches 2 of a polynomial. You just plug 2 into that polynomial for that limit by what we had on the previous slide. And we get 2 cubed minus 4 times 2 plus 1. And now we have just two much simpler limits up here to work out. So the limit as x approaches 2 of x squared is 2 squared. And for this limit right here, remember the limit can come inside the radical. We'll put it inside the radical here. And now there's only one limit left in this problem. The limit as x approaches 2 of x minus 1. Well, that's a polynomial, so just plug in 2. This limit is equal to 2 minus 1. So now we've got it all down to just plain numbers, add them up, and you get 12. So this limit is equal to 12. And we got that with limit laws. Now, sure, you can look at this and you can say to yourself, well, what is this limit equal to? Well, it should be what you get when you plug in the number that x is approaching wherever you see an x, and that's exactly what we got down here. So it's okay to look at it that way, but it's also important to understand these limit laws because there are going to be times coming up soon where it's important to think about things in terms of limit laws. A couple of comments. One is that variables other than x are common. I use x a lot because it's just, we think of x as being a variable, but you could have the limit as z approaches 2 of this expression, where x's are replaced by z's. It doesn't really matter what the variable is as long as you're consistent. This is going to work out to 12, just like it did here. Here's another one. The limit as x approaches 1, the limit as h approaches 1 of 2 minus 2 over h. So you can reason this one out. H is the variable. It's getting closer and closer to 1. What's happening to 2 minus 2 over h? It's getting closer and closer to 2 minus 2 over 1, which is 0. So here we've just kind of reasoned that out without applying any limit laws. But if you applied the limit laws, you'd get the same thing. So keep in mind that you're going to have limits with variables other than x. That's pretty much it for today, but I do want to say a few things about these limit laws that we talked about. First of all, a lot of times I'm going to combine these first two limit laws. They're kind of redundant, and rather than listing them separately, I'm going to put them all together like this, both of them together. Limit as x approaches c of f of x plus or minus g of x equals the limit as x approaches c of f of x plus or minus the limit as x approaches g of x, where it's plus or minus here and here, depending on the problem. And it almost goes without saying that This applies not just to two functions, but any number of functions, like the limit as x approaches c of f of x plus or minus g of x plus or minus h of x equals the limit as x approaches c of f of x plus or minus limit as x approaches c of g of x plus or minus limit as x approaches c of h of x, and so on. So the important takeaway today is we have some limit laws that help us find limits. So get some practice with that, because coming up, we'll see situations where things are a little more complicated. We're going to look at finding limits algebraically in Lecture 9. And in that setting, it will happen that, particularly with this limit law, it's not going to apply because the bottom turns into 0. And so you're going to have to do some algebraic cancellation to make that work. That's coming up in Lecture 9. Work some exercises, and I'll see you soon. Goodbye.